Okay, so this is where we have finished in our previous lecture. We have derived this expression, the swing equation for synchronous machine, m d2 delta dt2 equal to pa. Pa is the accelerating power, m is the angular momentum, and delta is the angle between the internal voltage, that means generated voltage, which is along the quadrature axis of the rotor, and the terminal voltage. So this delta, obviously it will be at steady state. At steady state it will be fixed. It will have a fixed value. Okay, fixed value. But whenever, that means at steady state, delta has a fixed value, means PA will be equal to 0. That means input power will be equal to output power. But whenever there is some disturbance, maybe in the form of change in demand or maybe in the form of some fault, then obviously delta will change because the speed of the machine will change. So the speed at which this phasor E and this phasor V rotate, there will be a difference because V is connected to infinite bus. Terminal of the machine is connected to infinite bus. Connected to power system means infinite bus, and the frequency there is fixed. So V is rotating at synchronous speed always. But you will be along the quadrature axis of the rotor. That means what will be the speed of this vector E, speed of this phasor E, it will be decided by the speed of the generator, speed of the rotor of the generator. So when PI is positive, speed will increase. When PI is negative, speed will decrease. Okay, speed will be above synchronous or below synchronous, depending upon the nature of PA. That means whether PI is greater than PE or PE is greater than PI. Okay. Now this, how much is the value of PA, that actually creates the main point of concern. That means if PA is very small, then change in speed will be very small. As a result, this will be a problem of frequency control. But if PA is large, the frequency problem is will not be a frequency control. Rather, it will be the problem of controlling the stability of the machine. It will be the problem of maintaining the stability of the machine. That means whether the machine will be able to retain synchronous speed or not, that will be decided by the value of PA, and that will be decided by some other factors that we shall discuss. Okay, now let us see what happens. Consider situation like this. What happens when there is a large disturbance? Let us investigate this, then we shall see how we can analyze this thing. Okay, consider a very simple system consisting of a single machine connected to infinite bus. In power system analysis, particularly in stability analysis, this particular model is very popular. That means a generator is connected to infinite bus. Infinite bus in this case, obviously, I told you already that it is basically the power system, and that system usually it will be so large, its capacity will be so large that with respect to a single generator, we may very safely consider that system to be acting as an infinite bus. That means a bus where a generator is connected, which is of infinite capacity. This is the basic meaning of infinite bus. Okay. Capacity of the generator, capacity of this system is very large with respect to the capacity of this machine. Okay. We are investigating the stability of this machine with respect to this machine. This system is very large, so we call this system to be infinite bus. Now, assuming that the generator was running at steady state, the power system was at steady state, and it was delivering some power to the system. Some power was being transferred from the generator to the system. How much is that power? To analyze this, to actually explain the situation, let us draw the power angle curve of this generator. Say this is the power angle curve. Power angle curve means P versus delta. It is the delta here, that means angle between the internal voltage, generated voltage, and the terminal voltage is being plotted here, and this represents the power output of the generator. Okay, P along the vertical axis, Q, and that this one, someone is entering. Okay, P along the vertical axis, along the horizontal axis is delta. So when the generator is delivering a power, say this much power is being delivered by the generator to the infinite bus. So this is the power angle curve. So this is the operating point because this is the input to the generator. Okay, that means this is pi, p input, and this is pe, p output. Obviously operating point will be the intersection of the input and output curve. Input line and output curve. Input is a line. Why it is in the line? Because it is a mechanical power input to the generator through the shaft from the turbine. This is the mechanical power input, and this represents the variation of electrical power output with the variation in delta. So operating point will be this one. Okay, obviously this will not be the operating point. Perhaps I have already explained why this will not be the operating point. If that is not clear, you tell me, I shall be explaining it today again. Okay, so this will be the operating point. Now, so at this point, we are assuming input power is equal to output power. So this is the output power curve, and cross section is, this is the intersection. So this is the operating point. So delta 0 is the operating angle at this steady state condition. Now, at this situation, input and output, they are same, and we are assuming that there is no loss inside the machine. So we are considering a lossless machine. So input is equal to the output. Now let us consider a situation where we are using a circuit breaker here, as if say to actually we shall be creating a fault, we shall be disconnecting a fault, because we want to impose, we want to imply some disturbance, and we want to investigate what is the impact of that disturbance on the generator. This is what is our intention. That's why we are creating a situation, artificial situation, say, where by the application of a circuit breaker, we shall be switching on the circuit breaker, and that will initiate a fault here. At the other end of the circuit breaker is connected to ground, because connected to ground. So if you switch on this end of the circuit breaker, then this bus will be connected to ground. When this bus is connected to ground, what will be the power output of the generator? Could you get my point? Say generator was delivering this power P to the system. This was power flowing. So this was the steady state. This is the power angle. This is the power angle delta 0 initially. Now you connect this terminal to ground with the help of a circuit breaker. We are using a circuit breaker because we want to control the instant of occurrence of the fault, and we want to disconnect the fault as well. That's why for controlling that, as if we are using the circuit breaker. Now as soon as we close the circuit breaker contact, that means as soon as the fault is connected, this is short circuited to ground, what will be the power output of the generator? Anybody, can you say what will be the power output of the generator when the this
Zero, zero, sir.
zero? Why it is zero?
Because sir, voltage is zero. No, VT is zero because it is short circuited.
Short circuited, and expression for power is
EF.
EV by X sin delta. Okay.
Yes, sir. Yes.
So whatever may be the value of delta, if B is zero, E is not zero. V is zero because now the terminal is grounded. It is zero, means the power output will be zero. But what is the input to the generator? At this instant, output is zero. But what is the input?
So steam input will be the remain same because
It will
we are
remain
not.
same. That means input remains same, but output jumps to zero here. So this is the situation. So from here, this will be the shift in output. From here, drastically it will become zero. So there is a difference now between the input power and the output power. And pi minus pe, that means input is more than output. That means the machine is will now accelerate. Speed will increase. Why the speed will increase? Because the turbine is giving a power input to the machine. Machine cannot deliver this power output to the power system. So where this power will go? This power obviously will increase the stored kinetic energy of the generator rotor. So speed will increase, and hence the input power will be stored in the generator rotor in the form of kinetic energy. So speed will increase. Okay, output becomes 0, so speed will increase. Somebody is entering, so let me take him in. Okay, so speed will increase, and as here speed will increase because this was input, this is the output, so speed will increase. As a result, delta will increase. Say delta has become from delta 0, it has become delta 1 here. That means some time has elapsed in between these two, uh, after the switching on of the circuit breaker. Then during that time, speed of the generator has become above synchronous. That means E is rotating at a higher speed with respect to V. Speed is above synchronous. Now E is going away from V because speed of the generator rotor is more than the synchronous speed. So vector E or phasor E will be moving away from the phasor V. So delta will increase. As delta increases, obviously power output does not increase. Power output does not change at all because it is connected to ground. This point is connected to ground. So output remains zero, but delta increases. Now let us assume that we have opened the circuit breaker again here. So when delta has become equal to delta 1, so what we have done, we have again say opened the contact of the circuit breaker. So this has been opened. As soon as it is opened, what happens? Now this terminal is not connected to ground. That means the terminal voltage is restored immediately because short circuit is removed, means terminal voltage will be restored. As the terminal voltage will restore, obviously, say field current we have not changed. As the field current has not been changed, so what will happen? Same field flux is there. Again, the power angle curve will remain same. So from here, as the circuit breaker contacts are opened, then operating point will jump at this delta 1 angle. Angle will not change immediately because change of angle requires some time, because obviously the rotating system, change in the value of delta will need some time. So as soon as del as soon as the circuit breaker contacts are opened here at delta equal to delta 1, then immediately output will jump from here to here on the power angle curve. It will jump on the power angle curve. That means from here it will come here. As this becomes the output power operating point, then what will happen? So output power will become more than the input power. Output power will become more than the input power. Am I clear? Could you understand this point? As soon as the fault is in applied, that means as soon as the circuit breaker contacts are closed, output from here will jump to zero. Why it will jump to zero? Because power output is zero. Now input power becomes more than the output power. As input power is more than the output power, speed of the generator will increase. It will become above synchronous. The rotor will rotate at speed which is above synchronous. So quadrature axis of the rotor, this along with this the E is inclined. Location of E, position of E is along the quadrature axis of the rotor. So as the rotor is rotating at a speed above synchronous, obviously vector E will move away from vector V. It is clear. You see whether this is clear or not. That means vector E will be moving away from vector V. Okay, is it clear? So delta will increase. So speed become above synchronous, delta will increase. As delta increases, output remains same. Output will not change. Okay. As output is same, so you see that uh, say at delta 1 is reached. So at delta equal to delta 1, let us close the contact of the circuit breaker again. At delta equal to delta 1, again the circuit breaker contactor say closed. Sorry, a circuit breaker contactor opened. So when the circuit breaker contacts are open, what happens? Operating point from here, it will jump on the power angle curve. So is this point clear to you or not? Is it clear that as soon as we open the contact of the circuit breaker, operating point will jump from this position to this position. That means from 0 to this position on the power angle curve of the generator. Is it clear? Could you understand this point?
Yes.
It will jump here. That means what happens if it jumps here? You see that here output becomes above the input. Output and now is greater than the input. So long output was less than input. Now output becomes more than input. Okay. Since output becomes more than input, what is the speed here? So long, what happened? Speed was above synchronous. So here initially speed was synchronous. As time passes, speed becomes more and more above synchronous. So here, when the circuit breaker contacts are open, operating point is here, but the speed is much above synchronous. Okay, as the speed is much above synchronous, though the output now is greater than input, delta will continue to increase because speed is above synchronous. Obviously, there will be a retardation of the rotor of the generator, but retardation from what point? Retardation from a speed which is already above synchronous. Okay, which is already above synchronous. So, speed of the generator again will start decreasing, but still it will remain above synchronous because so long generator has accelerated, speed has become above synchronous. So, from that value, speed will start decreasing, but it will take some time to restore the synchronous speed. Okay, so before the synchronous speed is restored, the speed will be above synchronous. So as the speed is above synchronous, it will again go again move away from the vector v. So that's why delta is increasing here. Speed is above synchronous, delta is increasing, but gradually the speed is decreasing. Gradually the speed is decreasing. Somewhere here say speed has become synchronous. We are assuming this somewhere here speed will again become synchronous. Why? Because the speed is will be reducing, it will be decreasing because output now is greater than input. And say at this point speed again has become synchronous. Okay. Now if the speed is synchronous here, you see that still output is greater than input. So for a moment, speed will be above just equal to the synchronous speed, but this will not be the stable operating point because here in our input and output they are different. Output is more than input. So moment after that, speed will decrease from synchronous. Now speed will become less than synchronous speed. As the speed is becoming less than synchronous speed, what will happen? Delta is increased to a maximum value. Now delta will start decreasing. Am I clear? Now delta will start decreasing from whatever value it has actually arrived at. From there, delta will start decreasing. So from here, as the speed is becoming less than synchronous, E and V will start coming closer now. Means delta will start decreasing. As delta is decreasing, it will follow the same path. That means it will trace the same path in the backward direction now. It will follow the same path in the backward direction. Am I clear? Is it clear up to this? Or any doubt? Anybody please tell me whether this is clear to you or not. Whatever I have actually discussed so far, is it clear to you or not? That means here the speed was synchronous, but after that, moment after that, speed will be below synchronous. Why speed is below synchronous? Because so far the machine was decelerating. Why it was decelerating? Because output is more than input. So there is less input, more output. From where the output will be given? Obviously, it is being given from the stored kinetic energy. That's why the speed of generator is decreasing. Okay, but as the speed of generator is decreasing here and still output is more than input, the speed will decrease further. It will go below synchronous. As it will be going below synchronous, what will happen? Now E and V will start approaching each other. They will be coming closer. Okay, because now E is rotating at a speed which is below synchronous. Okay, and V is rotating at a speed which is synchronous. So they will be coming closer. So delta will decrease. As delta decreases, what happens? Now obviously power output will follow the same path. It will trace the same path in the backward direction. Okay, using this path, the output power will decrease. So we shall stop tracking the delta at this point. Why? Because in our previous lecture we have mentioned that we shall be interested in the fast swing only. That means speed is increasing, delta is decreasing, and then delta is increasing and then delta is decreasing. So this is the first swing. Delta is increased, now it has started decreasing. So we shall assume that if the system is stable, then it will be stable at the first swing. This is an indication that delta has increased and it has started decreasing. So this is an indication that the system will become stable. We shall accept this. That why shall I accept this? Because we want to remain somewhat at a simple situation. We want to see complicated things we shall see later on. But initially, let us assume that system is simple. Only it is the generator which is responsible for increase in speed or decrease in speed. Any disturbance is only responsible. Other swings are not important to us because we are considering a situation when a generator is connected to infinite bus. So since the generator is connected to infinite bus, there is no other, you can say there are other rotating mode there. So there is no other oscillations, no other change in speed. So if the generator delta increases and then start decreasing, then you can say that this is an indication that the system will become stable because we have investigated the first swing. In the first swing, the tendency of the generator is to retain synchronism. Why? Because the speed has become above synchronous and then it has decreased, it had become synchronous, and then it has started becoming less than synchronous. Okay, so first swing is completed. So this indication that speed increasing and then decreasing, this is an indication that generator will become synchronous. Generator will be restoring the synchronous speed at the new steady state, and we shall be believing in this hypothesis now. Okay, now, if this is the situation, now let us investigate this in further details. So, up to this, do you have any question before I proceed further? Do you have any question here? Whatever I have discussed? Anybody? Anybody? All of you could understand whatever I have discussed so far? What
Sir,
was the
from,
question?
sir, from delta 1 to delta 2, you said that speed is decreasing, but load angle is increasing. So how speed is decreasing? If speed is decreasing, then load angle should also decrease.
No, you tell me. Repeat the question because I could not follow because the sound
Sir,
is problem is there. Huh,
from delta 1 to delta
huh,
2, you said
huh.
that the speed is decreasing from
Now,
above
speed is
synchronous.
decreasing from what? You see that initially from delta 0 to delta 1, what was the situation? Input was more than output.
Yes, yes,
So at delta 1, speed is much above synchronous. Is it clear?
yes, 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 yes,
Speed is much above synchronous. Now, here what happens? Here now, output is more than input. Since output is more than input, obviously there will be retardation. But from what? Retardation from what? Which situation? From the situation when the speed is much above synchronous.
yes,
Am I clear?
yes,
So
yes.
speed will decrease from that value. It
Okay,
will decrease from a speed which is already above synchronous, but still it is above synchronous. It is decreasing, but still it is above synchronous. So, since the speed is above synchronous, obviously delta will continue to increase. Obviously, the rate of increase will be now slower. Okay, rate of increase will be slower because the machine is retarding. But retarding from what condition? From a condition when speed is much above synchronous. So it will take time before the synchronous speed is restored again. And that has happened. Delta has increased, but speed is decreasing. Okay, decreasing from above synchronous value. Now, in this way, delta has continued to increase, speed has continued to decrease, but here the speed has become synchronous again. Say,
yes,
but Now, since the speed is equal to synchronous, what will happen at the next moment? You see that here output is more than input.
Yes.
So obviously the machine is retarding. So it will retard from what value? From the synchronous speed it will retard. So speed will become below synchronous now. Now as the speed is becoming below synchronous, now delta will start decreasing. From what value? From the value that it has actually achieved. Okay, previously it has achieved that a value, say delta 2, it has achieved that, that is the value of delta 2. From delta 2, it will decrease now. When decreasing, what will be the path followed by this machine? What will be the power output then? Obviously, power output has to follow this power angle curve. So it will be here. Why power output has to follow this power angle curve? Because we are assuming that field current remains same. So induced EMF remains same. We are assuming the terminal voltage remains same because it is the infinite bus voltage. So and machine reactance also remains same. So E same, V same, BT same actually, and synchronous reactance is also same, or machine reactance is also same. So obviously power angle curve will remain same. So while decreasing the value of delta, it will actually follow the same power angle curve. That means it will trace the same power angle curve here along this line. Okay, is it clear?
Yes, sir. It's clear.
Now let us concentrate on this region from delta 0 to delta 1 and then from the delta 1 to delta 2. You see that here it has been shaded like this and this is given a name A1. Also above this power input line and below this power angle curve another area A2 we have marked here. So this is an area A2 we have marked. This is an area A1 we have marked. From delta 0 to delta 1, above this 0 line and below this odd input line, this is A1. And from delta 1 to delta 2, above the power input line and below the power angle curve, this area is identified as A2. Now, what is this area A1? What does it represent? This area 1. Obviously, this power input and this is power output. Input is more than output. Okay, so though we are actually marking this point as delta 0 and this point as delta 1, from delta 0 to delta 1 there was some time elapsed, some time was needed for the machine to make the power angle curve from delta 0 to delta 1. That time is there. So during that time, this was the input power, this was the output power. So this area obviously is representing the area, representing the energy. Which energy? Energy input to the machine minus, sorry, power input to the machine minus power output to the machine. That means accelerating power multiplied by the time between for delta 0 to delta 1, this movement. Okay, that time. So obviously this A1 represents some energy. Which energy? This is the energy that actually has been stored in the rotor of the generator, because during this time the speed of the generator has increased. So as the speed of the generator is increased, kinetic energy has increased. So from where kinetic energy has been actually extracted? From the input power to the machine, and output power was zero. So total power input to the generator, it was actually stored in the rotor of the generator. Okay, and that kinetic energy is indicated. That means the representative value of that kinetic energy is uh, here given in A1. Is it clear? Could you follow this? Can I say that? Can we say that A1 represents the, somehow it is representing the kinetic energy? Okay, obviously the power is megawatt and it is a difference in angle is in radian. So megawatt radian, it should have been megawatt second. Now we are expressing this in terms of megawatt second. So in radian from delta 0 to delta 1, some time was elapsed. So this movement requires some time. So obviously this power multiplied by that time is the energy. But here we are showing between power and delta. So we can say this is representing energy, but here we are using it is some representation of energy, not in the actual unit of energy, but here we are expressing this in terms of megawatt multiplied by second. Am I clear? Megawatt multiplied by radian. Is it clear? Could you follow this?
Yes, sir.
Bolo. Okay, now you come from for see this area from delta 1 to delta 2 this time. Again, machine has moved from delta 1 to delta 2, rotor angle from delta 1 to delta 2, it has arrived. So what was the situation under this condition? Under this condition, this is the power input line P, and this is the power output curve. Okay, between this, because delta was changing, so output was along the power angle curve. So from here to here, this is the power angle curve. So between these, the power output curve and power input line from delta 1 to delta 2, this is again another representation of another energy, representation of energy somehow, and this is again in megawatt second, megawatt radian, not in megawatt second. We cannot express it in megawatt second because we are not plotting against time. Okay, we are plotting against delta. Okay, purposefully we are plotting against delta. So since we are plotting against delta, it is some way representing the energy associated. Okay, but here the unit should be written in megawatt because power is in megawatt, or difference also in megawatt, that multiplied by angle difference radian. So megawatt radian. So this is somehow representing the may not be actual energy we are talking about. Okay, but it is a representation of energy. It will be proportional. Simply you convert that into time, it will be the energy. So this A2 here you see that is again representing some energy. Is it clear? But what energy? So this energy A1, you see that this was actually injected into the machine as if, because power was supplied, power was given as input to the machine could not deliver any power output. So it was as if some power injection by the generator turbine to the rotor of the generator. Okay, it was some power injection, and because of this, generator could store energy. So power injection from outside. Now, what is this area A2? It is the power extraction, extracted power from the machine. Why? Because the power output is more than power input. So where from this power will come? Obviously, it will come from the stored kinetic energy. So as the the output was more than input, obviously kinetic energy has become reduced. Gradually, it has been reduced, and here speed became equal to synchronous speed means stored kinetic energy became equal to the rated kinetic energy of the machine. All right, kinetic energy here at this point became equal to rated kinetic energy of the machine, but moment after that again the speed decreased. So again the more and more kinetic energy was being extracted from the machine. So that second swing we are not discussing here. Okay, if you consider the first swing, so you see that here up to arriving at this value delta 2 from delta 1, so this area A2 represents the energy extracted from the rotor of the generator. Is it clear that A2 represents the energy extracted from the rotor of the generator? Is it clear?
Yes.
Clear anybody or any confusion? Why we say that it is the energy extracted from the machine? Because output was greater than input. So from where the generator will deliver this power? There should be some source. What is the source? Source is that stored kinetic energy. So kinetic energy is reduced. Generator has given power output, more power output than input. So it has caused reduction of the stored kinetic energy. So we can say that kinetic energy has been extracted from the machine. So from delta 0 to delta 1, kinetic energy has been injected into the machine. Energy has been injected into the machine. Here at delta 0, speed was synchronous. Here at delta 2, again the speed is synchronous. From delta 0 to delta 1, kinetic energy was injected into the machine. From delta 1 to delta 2, kinetic energy was extracted from the machine, and again the speed has become synchronous. Is it clear? Is it clear, or any doubt? Anybody? বলো কারো কোনো ডাউট থাকলে বলো, or it is clear to you, or you could not follow this. বলো.
Yes, sir, it's clear.
Yes, sir. Clear.
Now, can you tell me what will be the relative value of A1 and A2? That means which one is greater, or they are equal? A1 is greater, A2 is greater, or they are equal? What should be the situation? Now note that here at delta 0 speed was synchronous. What was the kinetic energy? It is the stored kinetic energy corresponding to that stored kinetic energy at rated speed. Again, here from here to here speed has increased. Here the speed is much above synchronous, and from that speed which was much above synchronous, speed has decreased, and again at this point, that means corresponding to delta to here, speed is again synchronous. So what will be the kinetic energy at synchronous speed? Again the rated kinetic energy. Here kinetic energy is equal to the rated kinetic energy. Here the kinetic energy is equal to the rated kinetic energy. In between, from delta 0 to delta 1, there was energy injection into the machine. From delta 1 to delta 2, there was the energy extraction from the machine. Okay. Now, A1 represents an energy which is injected into the machine. A2 represents the energy which is extracted from the machine. Now, can you can you imagine any relative value of A1 and A2? Which one should be higher, which one should be lower, or they will be same? And what is the logic behind? Whatever may be the answer, what is the logic behind that answer? Can anybody tell me? Bolo. Could you get my question?
Yes, sir.
So what should be the value of A1 and A2? On a relative value, not the exact value. That value we cannot say, obviously. It will depend upon the machine. Okay, and the value of delta 1, delta 2, etc. But whether A1 and A2 they are different or they will be equal. They should be equal or they should be different. And what is the logic behind? Obviously, some answer should be there, but what should be the logic behind that answer? Anybody? Any guess at least? Guess got a bhul hote pare, hok bhul, but can you guess something
It should be
regarding that?
equal because
Equal.
energy cannot be produced or produced. So the energy conversion law conversion
Yes.
law, what will be the stored energy? That will be
Okay, because at delta 0 speed was synchronous, so energy stored in the generator rotor obviously is equal to the rated kinetic energy stored in the machine. Okay, at delta 2 also kinetic energy obviously will be equal to the rated kinetic energy of the machine. Why? Because again the speed is synchronous. So in between, from delta 0 to delta 1, energy was inserted into the generator. From delta 1 to delta 2, energy was extracted from the generator. Obviously, to restore the synchronous speed, we must extract the same amount of energy that has been inserted into the machine, because energy, where from otherwise the energy will come, or where the energy will go. The machine is not lossy machine. We have neglected the loss, which are saying that the machine has no loss. So any energy that has been given as input to the rotor of the generator, that has been inserted into the rotor of the generator, must be extracted out of the generator to restore the synchronous speed. Since at delta 0 speed was synchronous and also at delta 2 speed is synchronous, obviously energy extracted must be equal to energy inserted. Energy inserted must be equal to the energy extracted. That means A1 must be equal to A2. That means synchronous speed will be restored again when A2 becomes equal to A1. We have assumed that here the synchronous speed is restored, but that is not a matter of assuming, because speed will be restored if and only if the energy, extra energy inserted in the machine has been extracted. Okay, then only the synchronous speed will be restored. Am I clear? That means synchronous speed can be restored if and only if the any extra energy which is given by A1, this extra energy has been completely extracted out of the rotor. And as soon as this energy has been extracted, the speed will be restored, synchronous speed will be restored. That means A2 will become equal to A1. Am I clear? বুঝতে পেরেছো? Is it clear? That means for restoration of synchronous speed, the energy has to be extracted out of the machine if previously energy has been inserted in it. Okay, and how much of energy has to be extracted? The energy that has been inserted into the machine. That means exactly the same energy has to be extracted out of the machine. Then only the synchronous speed can be restored. Am I clear? বুঝতে পেরেছো বলো? Or any doubt? Anybody,
Sir,
if you হ্যাঁ, আর কোনো ডাউট নেই কারো? Anybody not having any doubt? Okay, if you are not making any question, then I shall assume that it has been understood by everybody. That means you see that here, what is the condition for the restoration of synchronous speed? Here it is needed that energy that means area A1 has to be equal to area A2, because area A1 represents the energy inserted into the machine, area A2 represents the energy extracted out of the machine. Okay, energy extracted out of the machine. All right, so since energy inserted has been totally extracted out, speed has been synchronous speed has been restored here. Am I clear? Synchronous speed has been restored here. This will not be a stable condition, but this completes the first swing. After that, the machine will start running at a speed which is less than synchronous. That is a second swing. We shall not investigate into the second swing now. We are talking about the first swing. So if we see that the generator speed has increased and then it has started decreasing after attaining the synchronous speed, it is starting to decrease the synchronous speed, then we can say that the machine will remain in stable condition. This is our hypothesis. Okay, then why this hypothesis we are discussing, we are assuming that we have explained, and if necessary I shall explain it later on again. Okay, but for the time being, assuming that this hypothesis is true, that means if the generator can sustain the first swing, then it will be able to sustain any other swing. So if it is stable in the first swing, it will be stable in the subsequent swing as well. That's why we shall be investigating upon the first swing only. In the first swing, we are observing that energy extracted is just equal to the energy inserted. And if this condition is true, then you can say that synchronous speed is possible to be restored by the machine. Am I clear? Is it clear to you? Okay, it is clear.
Yes.
Now let us assume that somehow we are delaying the operation of this circuit breaker. Why after delta 1 the machine was delivering more power? Because we have opened the circuit breaker here. Now let us delay the opening of the circuit breaker. Okay, delay the opening of the circuit breaker. So from here at delta 1 we have not stopped. We have allowed the circuit breaker to be closed for some more time. That means now area A1 has become somewhat more. So this is area A3. From delta 0 say it is say somewhat other value of delta. Okay. Here now this area A3, again this is representing the energy inserted into the machine, and this area is appearing to be larger. Why? Because we have allowed more time before opening the circuit breaker again. So we have kept the circuit breaker in closed position for some more time. As a result, obviously this is the area A3. Okay. Now let us assume that here it is written delta CR. Say it is delta CR. Say this is the new value of delta. It is delta CR. At this angle, we have again opened the circuit breaker. So we have closed the circuit breaker at delta 0. At this angle, when delta has become equal to delta CR, then the circuit breaker is again opened. So as the circuit breaker is open, again this will be the operating point. Again, following the same logic, generator output is becoming more than input. So generator will start decelerating, speed will start decreasing. But from what value? From the speed it has attained, which is much above synchronous. So from that speed will decrease, but again it is still more than synchronous. So delta will continue to increase. As delta will continues to increase, so here at this point, so when input power line and output power line have just crossed here again, say have just meet here again, say let us assume that just at this point the synchronous speed has been restored. Let us imagine that just at this point synchronous speed has been restored. Okay, it is possible. We have adjusted the opening and closing of the circuit breaker such that we are arriving at the synchronous speed just at this point when input power line and output power line are just meeting at this point, and after that input output power line will become again less than the input power line. Just at this point synchronous speed has been restored. Okay, this is also possible. Is it clear? So if you could understand this situation, this scenario, obviously you can understand this scenario also. Here, whatever we have done, only thing is that we have delayed the opening of the circuit breaker here. So instead of opening the circuit breaker contact at delta 1, we have allowed some more time to, and we have kept the circuit breaker contact closed for some more time, such that when delta CR is reached, we have opened the circuit breaker contact. And as the circuit breaker contact are open, again output power becomes more than the input power. As the output power becomes more than the input power, what happens? The machine start decelerating, speed is decreasing. But from what speed it is decreasing? It is decreasing from the largest speed it has achieved at, arrived at. So from that speed is decreasing. It is decreasing, and say here at this point, which is basically pi minus delta 0. Because why pi minus delta 0? Because this is the power angle curve, this is the power input line, it is crossing cutting these 2 points. So if it is delta 0, obviously it will be pi minus delta 0, because it is basically symmetrical on the both half. Okay, that's why pi minus delta 0. So say at this value of delta, that means pi minus delta 0, the synchronous speed has been restored. So obviously this is a possible situation. Am I clear? This is a possible situation. We can adjust somehow. Say somehow we have adjusted this, and this is possible. Is it clear? Would you understand this?
Yes, sir.
Yes.
So again, here also A3 and A4 will be same. Why A3 and A4 will be same? Because A3 represents the energy inserted into the generator. A4 represents the energy extracted from the generator. At this angle, speed is synchronous. At this angle also, speed is synchronous. That means at delta 0, speed is synchronous. And at pi minus delta 0, again, speed is synchronous. So obviously, energy inserted into the machine must be equal to the energy extracted from the machine. That's why A3 and A4 must be same. That means these two area, A3 and A4, must be same. Okay. Now, If we delay the opening of the circuit breakers still further, what will be the situation? If we delay the opening, say for a very short while, we are delaying the opening of the circuit breaker, then what will happen? So instead of this position, say it has been allowed to move at this point. So will the generator be able to restore the synchronous speed again? If this is done, that is, if A3 is allowed to become somewhat higher, somewhat larger, will it be possible to obtain this area A4 where the energy will be extracted and A4 will become equal to this total area A3? Will it be possible again? That means if you allow A3 to become somewhat higher, then obviously A4 will be reduced from this value. So A4 will require some more area to match A3. But where this area will be obtained? Because after reaching this point, you see that since the speed is becoming uh, synchronous and here A4 is less than A3, what will happen after that? After that, you see that output will become less than input. If the output become less than input, what will happen? Machine will accelerate again. As the machine is accelerating again, the speed has become just equal to synchronous, but it will start becoming above synchronous again. And as it is becoming above synchronous, obviously delta will increase and output will decrease further. Output is decreasing. That means speed is stored kinetic energy is further decreasing. Machine is what is happening? You see that in output is decreasing, input is more. That means speed is gradually increasing, delta is increasing. So delta has not started decreasing here. It is continues to increase. That means it indicates that the synchronous speed will not be possible to be restored by the generator. Generator cannot restore the synchronous speed if we actually allow further delay from this angle delta CR. So we can say that delta CR, or rather say this is the delta critical. That's why you have written CR here. Delta critical, it indicates an angle after which we cannot we cannot actually afford to delay the opening of the circuit breaker further. We cannot insert more energy into the rotor of the generator. Then it will lose synchronism. Then it will not be able to restore the synchronous speed again. Okay, so this indicates the limit up to which we can actually delay the opening of the circuit breaker, or opening, we can delay the clearing the fault from the system. Okay, here a fault has been applied, here the fault was cleared. Now here the fault is cleared at this point, but if we delay the clearance of the fault further, then the generator will not be able to restore the synchronous speed again. Is it clear to you? All of you, is it clear or still some confusion? Bolo. Any doubt? Bolo. কোনো ডাউট
No,
থাকলে
sir.
বলো। No. That means you see that we cannot delay the opening of the circuit breaker here. That means we cannot delay the clearance of the fault. Fault has generator speed was increasing. Why it was increasing? Because of the application of the fault. And as we have cleared the fault by opening of the circuit breaker here, as we have cleared the fault, then the synchronous speed was again restored. But if we delay the clearance of the fault further from this point, then it will not be possible for the generator to restore the synchronous speed again. That means the generator will not be able to maintain synchronism. Okay. So what is the situation you are observing here? You see that for restoring synchronism or for maintaining stability of the generator, it is required that two such areas. One is the accelerating area another is the retarding area, you can say. Here it was available. A1, accelerating area, representing the energy that was reason for acceleration. A2, area representing the energy reason for deceleration. Again here at A3, it is the area representing the reason for acceleration, and A4 another area that is reason for the deceleration. A3 is equal to A4, A1 equal to A0. That means two such areas are required to be available, where one area represents the energy inserted into the machine, another area represents the energy extracted from the machine, and these areas are possible to be available here in this situation and in this situation, and the machine could maintain synchronous speed again. Machine could restore synchronous speed again. That means, and if we delay this clearance of the fault further, then the machine cannot restore the synchronous speed. That means for maintaining synchronism, for maintaining stability under large disturbance, it is needed that two such areas must be available to the system, where in one area this represents the energy inserted into the machine, and this area represents the energy extracted from the machine. And from this criterion, the name is given the equal area criterion. That means for maintaining transient stability, two such areas must be available. One area representing the energy reason for the acceleration of the machine, another area representing the energy extracted from the machine, and this is the reason for the retardation. And these two areas must be same. When these two such equal areas are obtained, then obviously the machine will be able to restore synchronism. And if this is not available, the synchronism cannot be restored, or the machine cannot maintain stability. Okay, hence the name is given equal area criterion. So this is from graphical representation. From this plot we have explained. Next day I shall actually develop the same with the help of some mathematical analysis. Okay, so we shall develop the mathematical relation in our next class. But here from this analysis we can say that if two such areas are available, one of area representing the energy inserted into the machine, and another area representing the energy extracted from the machine, and if two such equal areas are available to a machine after a disturbance, then the machine will be able to restore synchronism. Okay, this is the criterion for equal area. This is called the equal area criterion for transient stability. Okay, is it clear to you? Clear, it is. Could you understand this?
Yes, sir.
Yes.
Okay, then I shall stop here today, and in the next class, therefore, I shall on Friday I shall continue. Okay, so let me call you roll first. Call your name first. Abhishek Mojumdar,
Present, sir.
Aditya Rai,
Yes, sir.
Ali Hamzan,
Present, sir.
Anirudh Anand,
Present, sir.
Ankit Joshwal, Arijit Pal,
Yes, sir.
Arnab Pal,
Yes, sir.
Dipankar Singh, Dia Rai,
Yes, sir.
Hasibur Rahman,
Yes, sir.
Konishka Boshak,
Present, sir.
Kaushik Maji, Manos Patra, Mujadid Alam,
Yes.
Yes, sir.
Mujadid and Manos. Okay. Then Ritam Khamaru,
Yes, sir.
Shankha Mitra,
Yes, sir.
Yes. Shreyas Khatri,
Yes, sir.
Mohammad Sohel,
Yes, sir.
Jishan Rahman,
Yes, sir.
Somnath Pal, Kaushik Maji. Okay. Okay, you are present. Somnath Pal, then Showdeep Sen,
Yes, sir.
okay, Saurabh Burman,
Yes, sir.
Shubha Shubhadeep Bera,
Yes, sir.
Shubhadeep, Shubroto Mahata, Ankit Joshwal, you are present. Okay. Supratim Nashkar,
Yes, sir.
Swapnil Kishku,
Yes, sir.
Ujjwal Haldar.
Yes, sir.
Okay. Anybody who could not respond previously? Somnath Pal, perhaps you have not responded. Then who? Some more people. Deepankar Singh. Okay, you are present. All right. All right. Okay. So let me stop today. And again, and Abhishek Mojumdar. Acha, okay. All of on Friday 4:30 I shall meet again. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.